Hello and welcome to the fifth installment of this video series on fields. Today we're going to talk about uniform fields, and specifically we're going to look at gravitational and electrostatic as per normal. And we're going to look at how the idea of force, work and potential energy tie in together with these uniform fields. Okay. Now, let's look at this picture of the Queen's Guard. Aren't they magnificent? But don't they just look all the same? Which leads us to our idea of what is a uniform field. Now, they're all wearing the same uniform, and a uniform field in fields is a field in which the direction and magnitude of the field strength is the same at every point in space. Okay, let's first of all have a look at gravitational uniform fields. And what we're going to have here is Newton flying in to the grounds of Cambridge, where the apple supposedly fell on his head. Now that's not historically accurate, but kind of makes a good story, doesn't it? Let's have a look at all these points in space now. So if we think of the Earth being close in, we've got these points in space near to the surface of the Earth, and we can draw vectors for different field strengths at different points. At that point there, it's 9.8 newtons per kilo, or if there was 1 kilo, there'd be 9.8 newtons of force due to gravity. So you can see here at every single point here in space, we have a gravitational field strength of 9.8 newtons per kilo. Okay, let's explain the idea of force and work now. So we know the force of gravity is equal to mg, or mass times the gravitational field strength. So here's the mass, and g is the gravitational field strength. Now we're going to explain this idea of work with gravity in that grey vector pulling down, and mg is the hand putting the force there. Now let's imagine that apple being pushed up against gravity, and assume it has the same speed at the start and at the end. We'd then say the kinetic energy is the same at the start and the end. Now, thinking about work will be the force occurring by the hand over a certain distance. Okay, so Newton's first law states that object stays at constant velocity if the forces are equal. So there, both the gravity and the pushing force are equal, and the force pushing up is mg, and over a distance h. So we can actually say the work done to push that up from there to there, assuming the same velocity, is mgh. Now that work is going towards changing the energy of the apple, or increasing its potential energy. Okay, so this work is imparted on the apple itself, and so the change in potential energy of the apple is just mgh. Now you should be quite familiar with this, but this is a sort of a derivation of how work here relates to the change in potential energy. So in this scenario, the work is going to the change in potential energy, not kinetic energy. Okay, let's do a fun fact now, and it relates to Sir Isaac Newton. Now, a fun fact about him is it turns out that he nearly didn't survive birth. So he was born 11 to 15 weeks prematurely, which is it's 40 weeks. And it's a lot shorter than that, and he was said by his mum to be able to fit in a quart-sized glass. Now that is tiny. Imagine he didn't survive, where the world of physics would be today. So he was lucky to survive, and thankfully to all us scientists he did. Okay, let's look at electrostatic uniform fields. Okay, now let's look at this example here of oppositely charged plates, which creates a uniform field. Now, if we draw all points in space here, not all, but pretty much some examples of points in space, we should find that in this uniform field, its uniform has the same direction and magnitude. The direction is always downwards, and the electric field strength itself, in terms of magnitude, is always 10 newtons per coulomb. Now let's go through an example using this oppositely charged set of plates. Now, in theory, they should be infinitely long, as in the plates are infinitely wide. Towards the edge of those plates, if they were a real distance, it's not quite uniform. Now, it's also known as a capacitor in electricity or electronics even. And the force, instead of the force being mass times gravitational field strength, in electrostatics, it's the charge in the field times its electric field strength. So that's analogous to the gravity example there. And what we're going to do is a similar example here. Now, the electric field on a positive charge is going to draw it away from the positive charge and down towards the negative charge. That's in the grey vector there. And the hand there is going to do work on that charge to push it up as so. So in terms of the force, it's going to be QE pushing up over a distance of D. So in this here, we can derive the work done, which is a force times distance, which was QE, times over a distance of D. Okay, so the change in energy on that little q charged particle will go towards being its potential energy. So the change in potential energy will be Q times E times D. Okay, so QE is the force and D is the distance. Now, up is positive in terms of its change in potential energy, whereas downwards will be negative. And that hand is resisting that motion of that force there. Okay, so a key idea is understanding when work is positive and when it's negative. When the movement is opposite to the field's force, we're kind of pushing against the force and moving it in the opposite direction. That increases its potential energy, so the work is positive. Now, conversely, the work is negative when the force being applied is resisting that motion, and that means the movement is in the same direction as the field's force. And that decreases the potential energy of the object. Okay, now let's go through an example here. We've got a 2 millicoulomb charge, and that's moved between a negative and positive plate with that electric field strength of 100 newtons per coulomb. The plates are separated by 3 centimeters. And what is the force on the charge, and what will the work done be, and the change in potential energy of the charge? Okay, now we're going to label, as we should do with all physics questions, we're going to label what the charge is, which is 2 millicoulombs, or 2 times 10 to the minus 3 coulombs, and we can see it move there from bottom to top. Just note, with this question, there's an external force being applied to move it from the bottom to the top, which is not changing the kinetic energy initially and finally. Now we've put in our values of D, 3 centimeters or 0.03 meters, E being 100 newtons per coulomb, and we can work out the force on the charge here. Now it's going to be Q times E, and Q is 2 times 10 to the minus 3, and the electric field strength is 100. So we get the force being 0.2 newtons. Now I've put down here, and that's the force due to the field itself, but the force being applied on the charge such that it moves upwards will obviously be up. Okay, so depending on the question, it might be a little bit ambiguous here, but I think I've clarified it there for you. Now the work is just going to be the force times the distance, which is QE times D. And we get 2 times 10 to the minus 3 times 100 again, times its distance. So just the force times distance there is 0.006 joules, or 6 millijoules. Now the work is positive there because we're increasing our potential energy. And our answer there for changing potential energy is positive 6 millijoules. Okay, now just to summarize this video, let's compare uniform gravitational fields and electrostatic fields or electric fields. Now, gravitational fields, again, for a uniform field, It's approximate, and this we can assume this to be close to the surface of a planet. Electrostatics, we need parallel plates of opposite charge, which are known as capacitors. The force in a gravitational uniform field is mass times the gravitational field strength. The force in in electrostatic is the charge times the electric field strength. And we can get the work, which is the change in potential energy, will be mgh in a gravitational example, and the change in potential energy in the work in electrostatic will be Q times E times D. Okay. And also that idea of positive work being positive change in potential energy, and vice versa, negative work resulting in a negative change in potential energy. Okay, thank you for watching today. I hope that clarified uniform fields as well as force, work, and potential energy. Please definitely subscribe to this series of videos, or the videos that I've put up, and definitely leave some comments or feedback here. So see you in the next video. Bye.